A couple of months ago, there was some emails circulating around that Network Rail weren't using the tamping machines that well. And if we're honest, that's true. So I set about putting a presentation together. Probably got a bit carried away and put about 800 slides. We'd have been here till tomorrow tea time, but fortunately Liam did a bit of an editing session, so I'm trying to fit it now inside 40 minutes. So what we're going to look at is OTM strategy, a bit on tamping parameters, how the actual tampers work. Main part of the presentation is tamping S&C, something I think we really struggle at in Network Rail, and hopefully, time permitting at the end, have a look at some of the technology on the 09 4x4. So first of all, we've got various machines in our fleet, and it's important to have the right type of machine for your particular route. We've got S&C machines, Placer 08 4x4 and B41 Matisses. Generally designed as S&C machines, but we hammer them a bit on plain line, do about 400 metres an hour. Then we move on to our higher speed continuous S&C machines, work about a third quicker on S&C, probably looking at 900 metres an hour plain line. Then our high speed plain line machines. I didn't actually realise some of the routes had these, 09 3Xs and 2Xs, 3 sleeper continuous tamping machines, very high speed, you're looking at 2,000 metres an hour. It's quite hard keeping up with them actually. I'm quite glad we haven't got them in our route. Plain line machines, we've got 08 compacts, does about 500 metres an hour. Got flexible times, but they're not an S&C machine. I've seen them use on S&C, and they're not an S&C machine. Very good for areas of guardrails, stuff like that. Finally, your stone blowers for your areas that don't respond to tamping, and any specialist technology you might want, sprinter tamping, curve assisted laser, DRP, DTS and System 7. Just I'll put these in though. To constitute an S&C machine, you really need three elements to it. You need to have split tines. As you can see in the top left, you've got horizontal and vertical split. You need tilting tines, and you really need a third arm lifting point for turnouts. Also, we spend a huge amount of money on our S&C, and we should really have a definitive strategy for it. I hear a lot of times, we haven't finished because we don't get that amount of time, or we never. And what we really need to do is take into account how many point ends, whether we want midweek, Saturday night possessions, which direction, a frequency. And what I did, we literally went through every junction and just identify exactly what you need. And the caveat was, look, I want 16 hours instead of the usual 10 or 12, but then I'll only tamp that junction once every 2 years instead of every year. So give me what? So it's better to do things better every 2 years and not properly every year. Just moving on. Possession hours as well. It's, particularly on our 4-line sections where we have complex ladders, just make sure you've got enough where you've got, sometimes you can have ladders where the two middle roads aren't connected, so you want your 2 outside roads and you want some time in the middle, or are they all connected and you want a rolling block. It's really important to get your detail right in your possessions. You get one hit at it and you need to do it properly. So I'll have a quick look at tamping parameters. I just put this slide in. Tampers aren't as complicated as what people think. It's basically an eccentric rotating shaft. You've got a cam that rotates. The cylinder assemblies squeeze outwards. It pivots on a point and consolidates the ballast under the sleeper. That's basically what they do. Moving on, you don't really need to know the top two items on there. It basically vibrates at 38 hertz, 35 to 35 hertz. 25 to 35 is the optimum, but we have to go up to 35 because we'd have trouble penetrating the ballast around 25, cause damage to ballast and component wear. Amplitude is 5 mil, so we generally get about 10 mil vibration. These are the things that you probably should keep an eye on. If the operators are good, we generally look at 0.8 to 1.2 second squeeze time, 0.8 for renewals, 1.2 on the maintenance side. Obviously depending on lifts and whether we're double tamping. Squeeze pressures should be in that threshold. But I did want to look at 2 things, magnitude of lift and time depth. Put a couple of graphs on here. This one is basically saying that after settlement, because when we lift or renew track, it settles down under dynamic forces of trains. And unless we're looking at 17 to 20 mil, we're literally losing all our lift. A couple of reasons for that. There just isn't enough room to reconfigure the ballast under the sleepers. And under track settlement, you're literally using all your lift, something we call ballast memory at times. So it's only when we get into the bigger lifts, about 25, 30, 35, that we really get that the settlement then becomes a less of a percentage of the lift and we get that durability. The problem is we have standards that, under wires that dictate 25 mil lifts and slews. And the problem with that is we're not lifting the high points, we're lifting our track faults. So the areas where we do need to lift over 25, our lower points, we're just not getting the opportunity to lift it. And therefore, we're losing a bit of durability. Similar graph, this is an empirical curve. I've used this when we've been using DTS a few times. Not quite the same, but it's sort of like putting the same message across, that your settlement starts to reduce as a percentage of your lift as you put more lift on. And this one, tamping depths, probably our biggest and easiest quick win. The amount of times I see us tamping at the wrong depth, it's quite incredible, really. Too shallow, and we literally cause damage to the tools on the machine. We damage the soffit to the bearers or sleepers. Too deep, and yeah, we'll pack it, but we lose durability. And all we need to do is measure the top of the rail to the bottom of the sleeper bearer or timber, and that gives us our construction depth. There is a list of them in TRK 3241. Machine adds 15 millimetres and off you go, and just on the screen you can see that's how simple it is. Mark it up so the operator can see it. He presses a button and it changes the depth. Right, moving on to how tampers work. I did have a couple of slides on 3 and 4 point lining, manual ways of using the machine, but they fell victim to the Liam Jackson slide cull. So unfortunately I can't. If anyone's really keen on that, they can give us a shout afterwards and I'll go through it. What I will look at is geometry and measurement and compensation, tiny bit on overlift. Just before that though, just a bit of tamping basics. A tamper will it'll have a datum rail where it measures and puts its adjustments on, and it'll have what we call a float rail where it applies the cross level or cant required. Yeah, so just be wary of picking the correct datum rail. The low rail on curves. On a straight, you want your highest or best rail. And what it also does, it uses a preload where it pushes its measuring trolley out on and you want it, well, the operators should know this anyway, but they always ask you what preload it is if you're doing a design, and it should be on the running edge of the outside of the curve. And just so people know, I just threw this one in for awareness again. The tampers don't actually apply lifts and slews at the working area. They basically apply it at the front feeler trolley. So it's why they're called front offsets and level corrections. So what basically happens is, for lifting, it'll apply your correction and it'll just basically straighten out its lifting chord or put the leveling transducer to 0. I've put transduce there, that should be transducer. And similarly with slews, or well, front offsets I should say, it basically moves the track over till it achieves its target versine. Tamper software, we got Placer machines, we got Win and Smart ALC now, and we got Matisa, which has TGS and Gecko on there. I can only really do Placer because we haven't got the simulation, we haven't got the program, the software of Matisa. However, we have got Gecko, and basically these do all your horizontal and vertical adjustments. On the 3 and 4 point lining, one of the problems with it is when you go through transitions, you have to do a lot of smoothing on the transitions because the tamper won't understand it. So you have to do a lot of manual calculations. And also on vertical curves, sags and hogs, you have to do, and also on a tight curve, it will pull the measurement trolley in and you have to do, so there's a huge amount of manual calculations that we used to do. Fortunately, software does it all for you now, so makes life a lot easier. So I'm looking at measurement and compensation. I reckon we use this probably 95% of the times, apart from West Coast ATG. And what happens is the machine traverses the site and it measures horizontal and vertical versines, and it basically smooths or compensates them. We can actually have a bit of influence on that. We can add our own elements. For instance, when it's going around a curve, we can actually set that curve to a single radii. Not a lot of people know that, but obviously provided we've got the sufficient slews to do it. So if you're having a curve that's a mile long, you know, it's a bit ambitious if you can only slew it 25 to have a constant radius curve, but there are options on there where we can do that. We could also put, vertically, we can put it to a specific gradient, obviously leaving up 20 or 30 metres between elements to give the track a chance to connect up. We can put virtual transitions in, these are optional. Cant transitions, they're a must. You'll know if you get there, if you don't put them in. We can insert tangent points on vertical curves if we know where they are. And also we can put fixed points in with tolerances, or we can put a fixed area in with a tolerance in. So we can have an area where we basically don't want a slew at all. We might put a 5mm slew one way or stuff like that. And then we enter the speed class of the track, and the machine will basically smooth out on that speed class. Now, there is a temptation, I've done it myself in the past before I really understood it, to put a higher speed class in because you get a better quality in your wood. But the problem is, if you're going around the transition, bear in mind that the transitions are designed for the rates of change for that speed. So the tamper, if you put a higher speed in, will think, hang on, there's a problem in it. It'll want to extend the transitions at both ends to make it smoother. So always put in the speed class that it's actually of the track you're on. And here's basically a slide of measurement and compensation. I've messed around with this myself. I've put in, so I'll just go through it. On the left, you've got your horizontal. So hopefully you can see a red line there, which is your measured versines. The green line is design. We move over to camp. As you can see, the camp follows the curve. And then we've got our level versines, and basically on the right-hand side, it shows you what speed that the track can go at. Now, hopefully you've noticed the bars on your left, they're SD values. So obviously you've got your green for good and yellow for satisfactory. Now, as you can see, I have put, those of you with keen eyes will see a brown bar on the very left-hand side, and that's where I've restricted the slew severely. I also put the speed category just for effect to make it really bad. But as you can see, the machine will always try to compensate in good, but because I put those restrictions on, we've got a satisfactory and a poor on there. Now, had I not put those, and this is to emphasise the problem of putting restrictions on, so we severely reduce the machine's capability to achieve good track. There's the speed classes, bottom right-hand side. So that is basically what you do on a measurement run. Right, moving on. Right, tampers measure on chords. Right, these are an isometric chord, which basically means it's not symmetrical. And tampers are generally more biased towards the rear chord, about a third, 2/3 to the front. Now, the problem is with using chords, there's a couple of problems. Tamper uses isometric chords because they're better on shortwave track. But what the problem is, if you have a look, if you can imagine that's a chord on, it's a bit of a busy slide, don't worry too much about it. What the idea is to try and show you a chord in a long wavelength. And the problem is, because the chord's inside a long wave defect, it distorts the amplitude and phase displacement. Phase displacement is just the angle. So it basically distorts the size of the defect and the angle that it's at, and this is known as the transfer function. Now, what ALC has got built-in algorithms, and they define the inverse transfer function, so they can actually compensate for this. So when you're inside a large, a long wave defect, the tamper can actually realise that and adjust it accordingly. And on top of that, it's got a factor algorithm. And this can basically, it was done, there was a lot of experiments and research that were done on it, and it was basically use a long optic over to do the results. But what it basically does, again, it uses a number of algorithms to extend the chord. So our tamping machines can work at 5 times the chord length, so we can actually correct defects of 90 metre weight. Generally starts to reduce at 90 metres, so by the time 95 metres comes, you're struggling, which is great for us because our long wave track is measured on 70. But one of the biggest problems is that we just constrain the machines. If we've got 25 lifts or 25mm slews over 70 metres, you've got that much over 70 metres. So this is why, when people wonder why our, ALC doesn't correct our long wave faults, it can. We just don't let it. And what it does, it's very clever as well. For each speed class, as I mentioned earlier, it measures on a series of hypothetical chord lengths. So if you've got a speed, say, of 10 miles an hour, it may do chord lengths of 5 to 8 metres. By the time we go up to 20, it'll do 7 to 10. As you know, so it does a series until it achieves good, and then it will compensate that. So it doesn't just measure and compensate, it actually gets the right chord length so it can get all the short and long wave defects. So as you can see, there's quite a lot more to ALC than what people think. It's a great system, we just don't let it work. And on top of that, we put our so not only do we limit the lifts and slews to 25, we then come in and put fixed points in, which severely restricts it even more. And the best one is when we're doing crossovers in S&C. Come to the crossover, most important point, and we'll put a fixed point in, and people say no slew here or 5 mil there. And so not only are you doing that, the tamper's got to ramp down. It can't just go to slew and 0 because we leave it. So if we're doing a 25 mil in S&C, but you've got a no slew or reduced slew, don't forget the tamper has to ramp down at about 1, well, it ramps down at 1 in 1,000, that's a default setting. So 25 mil is 25 metres of ramping down, and then it's got to ramp back up. So by putting fixed points in, we're just severely restricting what these machines can do. Very quickly, yeah, the machines have got all the network rail SDs imported in. The only problem is that the tamper SDs are Versine derived and the network rail ones are inertia based. So it's apples and oranges to an extent. They're similar, but if you get good on a tamping machine, don't be surprised if you don't get good when the NMT runs along it, because they are slightly different, but it definitely gives you an idea. Right. And so this is measurement and compensation. We've compensated it. This is it in work mode. As you can see, the left-hand side is the horizontal that I've said, so they're the Versines. And you can see where I put the brown bar. And you can see I restricted that to 5 mil. And you can see the front offsets in the next box. They're basically, and that is why we had our poor and, that's why we had our satisfactory and poor rate. In the middle is the cant. And the two right-hand ones are the level and the lifts or level correction required to achieve it. Okay, so I've actually shot through measurement and compensation in about 2 minutes. I took some of that in. The bottom line is it's a much better system than what people think. We just don't let it work. We restrict it to 25 minutes, and it's something as we've got to discuss as an industry. Do we need to have a look at that, because we're only lifting the low point? So by putting 25 mil in, we're massively reducing our effectiveness. Maybe something we need to discuss. Moving on to geometry tamping. We basically need a design for this, and we generally do a geodetic survey. We use a symmetrical chord, generally 20 metres. This is better for long wave stuff, particularly around 40 metre defects. We might use a theodolite level, total station, and we have various kit to help us do this. And once we've done a design, all we do is just input the design. So on the left-hand side, again, it's the horizontal. So that is basically a right-hand curve going into a reverse curve. You can see the cant in the middle reflecting the reverse curve, and you've got the vertical on the right-hand side. So each line is a gradient change. The boxes on the left are sags, and the boxes on the right are hogs, and you can see the curve radii. So you can enter that by pressing on the graph and putting an element in, or doing it in the table. Much easier to do it on the table, actually. Same with Versine, same with front offsets, level corrections. You can either enter them on the graph, or you can do it in a table, or there is a cheat mode. One of the lads on the West Coast actually devised an Excel spreadsheet where you could could directly import them into there. And fortunately, it was about 17 years after we've been using it, but I suppose better late than never. Geometry working mode. So I've put the vertical calculations on there. Yeah, they're the ones that we would have had to do in manual mode if we were 3 and 4 point lining. But as you can see, you should start hopefully getting used to this now. The horizontals on the left, then we've got our cant, then we've got our level, and then we've just got our front offsets and level corrections. And that's basically geometry in working mode. This is Matisse Gecko, so it's the equivalent, Matisse's equivalent of WinALC. As you can see, not as user-friendly, takes a bit more getting used to. A couple of things you've really got to watch, actually. Matisse Gecko works in kilometres, whereas ALC is metres. And also, crucially, you have to put the full vertical curve length in Gecko, whereas in WinALC it's half the curve length, so obviously don't get them wrong. And finally, both of them, the gradients are parts per thousand, and we design in percent, so always times it by 10, basically. Right, moving on. Why use geometry? When we get precise control through structures, it's absolutely essential for S&C. Anything that's tied, we need to know what we're doing with one road, so we get coplanar timbers, and we get slews that are harmonious. Also good for palliative lifts. We used to do a lot of these quite a few years back where we'd have formation failures. We used to lift the track by about 4 to 6 inches, probably unheard of now, coming with a ballast train, and that was a good life extension exercise. Also good for advanced tamping. Obviously, the staff that work on the ATG couldn't do their job without geometry. Good for MSAT, curve-assisted laser. We could also, using some of those formulas that I pointed out really on the graphs, design overlift. We can actually do a design and then predict what overlift we can put on. And obviously, because it's improved quality, it's less intervention, greater durability. We don't have to mark up the track. Anyone that's worked with an 07, it's a bit of a nightmare, actually. You had to put all the slews on the sleepers, right, all the lifts on the rail, and you had some poor soul trying to wind them on in the tower, and you look behind the machine, it was like that, and you just used to wait till you got the relief come on. It was an absolute nightmare. And the cost is minimal, it's free, it's built in on the machine, so it's there. So this is one, yeah, this is just to do with a design that we did using Clearroot. This is an interesting one. Those with keen eyes will probably make out a steam train. And we had to slew this, we had to slew one track out the way 8 inches so we could slew the other track out into the right position to get the steam train through. Anyway, we did this. I did this in one pass, actually. These are the days when you could do that, by the way. Yeah, just I saw a few wry smiles there. Now it's basically where you're allowed 75mm lift, 75mm slew, and 50mm cross level correction. So please don't go saying some bloke from Weston said I can move the track 80 because it's not the case now. Anyway, we basically got that in one go, and just a couple of weeks before the job, there was a rail defect, quite an old. It was 1968 F19 actually, a pretty old track, and of course it was riddled with defects, £109 rail I think. Anyway, they took the defect out, and the usual didn't have time to re-stress it, you know, so they had to put it back in as a red item. But we'd actually come in and slewed it, and we'd slewed it that much that when the lads come in, when the staff come in to re-stress it, they actually cut into it, took the stress-free temperature, and it was 26.7 degrees. So if I'd have known that, I could have sent out a job number for that and got some money for it, but there you go. So yeah, it's an interesting story there. And it's really good for designing crossovers, really easy. Just get your tide area on a crossover. So calculate, so you design your low rail first, dead easy. I did an example here, so on 65mm a cant on a standard interval. Your 2 low rails is 151mm difference. So what you do is you design your bottom rails, and then you just add 151 or whatever it is, and then you just design in and out of it. Very easy to do, and gets all your bearers and timbers coplanar. Overlift. Now, overlift is basically where we design above our target area, so just to compensate for settlement, what we spoke about earlier, and this gives us our durability because we're actually taking into account how much the track will settle, so it will settle in a place. If we just design it to where we want, after settlement, it will be below, so it's just taking that into account. We got various ways of doing. We can, like I said, we can just design our own overlift using our design. We can use it, various ones on the machine. When ALC, you can do a percentage of the lift, or there's a BR graph on there from 1960s, I think, some research. The new 09 machines have smart ALC, where this has a percentage of the lift, or you can do a mean value rolling over 30 metres. So basically anything under that mean value gets overlifted to that point, or you can do a percentage of that. We've got intelligent overlift DTS, which is done on recent research about settlement after DTS. We've got the older DTS machines, the 09s, they've got a slightly different system from older research. And finally, we've got an overlift option on the Sprinter or spot tamping. I haven't got time to go through Sprinter, tamping or overlift in detail, but as the communities of practice run by Gary Smith, I was hoping Gary would be here actually, I'll point it out, but he's probably skulking around the screen in Tamworth somewhere, so he's got away with it actually. But hopefully we'll be getting, we'll hopefully have something done by August, so if anyone's really interested in Sprinter and overlift, we'll have a definitive guide then. Yeah, I hope, yeah, I'm sort of like blowing you out the amphitheatre at the moment, but I am trying to cram quite a lot in. So we're moving on to S&C tamping now. Now, first of all, tamping parallel. So we're doing this on, so I was actually supposed to take them pictures out, wasn't I, Liam? I didn't. Anyway, I didn't know that's still there. Anyway, tamping parallel. Traditionally, we used to do this with one machine, and you know, we used to use a third arm, not designed for a crossover, right? It's designed for a turnout. So what we used to do is basically open fastening. We used to think we were getting cross levels. We were opening clips, we were ruining clips, and then as soon as we let go, it fall back down. It's labour intensive, time consuming, and accurate. Basically, if it's a crossover, don't use one machine. That's the message I'm trying to get. Use, yeah, it's Neil Denton joined us there as well. It's very nice of him, isn't it? Yeah, so if we're using basically 2 machines, yeah, And what you've got to do is connect the machines up. Now, if you've got a layout with high resistance fastenings, concrete bearers, say if you've got E+, fast clip or something, then what you do, connect the machines up and they'll lift together harmoniously, but basically you have a primary and secondary machine. The primary machine will be the one that slews, and you turn the slewing off at the first tied bearer and turn it back on at the last. So basically they both lift, but the primary machine slews, yeah? And that's what it says in the standard. However, and this is not in the standard, if you're doing an old timbered layout or an aging concrete layout, you might have some shuffle, base plate, rail gore, you have lower resistance fastenings that have probably been in, God, you know, before we were born. If you're basically doing slews, say if you had a 25mm slew through the tied area, because of all those issues, you are not going to get 25mm on the other road. So by turning the alignment off, you will end up with a misalignment. So you've got to make a judgment. And in this case, what we basically do is lift harmoniously, but slew independently, but obviously try and keep the slews in. And every now and again, they'll be fighting each other. That's basically because you might have gauge problems or some of the problems in there. So just be very wary. What the standard says is great for renewals and it's great for new layouts. But I tell you now, and there's people that are watching around the country who know that it does not work on these layouts and you end up with a misalignment in there. So fine, this is just basically saying, yeah, use machines independently, but just be wary, try and keep your slews within 5mm. Right, move on to tamping turnouts. A bit more to this, it's more difficult to tamper turnout than a crossover. What we traditionally do is we got a blue route, we do the through road and then we do the turnout road. And what happens is, again, we get the third arm out. The limits are there. For plasters, it's 2.1 metres, for Matissa, it's 1.9. And again, we lift it up and the fastenings deflect, they open. And again, the same thing is we let go and it falls back down, even though on the machine it said that we got the cross level because we're basically opening clips. And what happens is where the track's tied, we've got that because we're not getting the cross level. As soon as we get back onto the plain area, we've got that. So we have cross level faults through the turnout and we'll have a twist on there. And I've seen that happen on numerous occasions. So I put together this colour-coded chart as you're going into S&C. The orange bearers you tamp conventionally, and then you get to the purple bearers, which what we call castle tamping, as you can see. It's basically where it goes through the rails, it looks like it's going through battlements. So what we do is where it's castle tamping, the machine can still lift and consolidate properly, so we just need to make sure we bring the tines out. However, when we get a bit further on, the blue bearers, we need a bit of assistance with it, so we bring out the third arm and some packing. So we've got, the castle tamping limit's gone now. So what we do, we get the third arm to help, but then the operatives come in and pack it, it's just basically to keep the cross levels because we'll come back with a machine and consolidate it properly afterwards. So we have to do that. And then as we go through, it gets to the stage where the third arm limit is reached, as I've said, and then we get to the green bearers. And the green bearers, we are literally relying on track jacks, so you need your staff out with jacks, and you literally jack up. You can actually put cant gauge on it, but I prefer to look at the level galvo, the centre galvo in the machine. When it's 12 o'clock, you've got your level. So you jack it up, hit 12 o'clock, lads come in, pack it, staff come in and pack it, and you can then move on. So as you can see, and then you get to your orange bearers on your plane, and you can just tamp conventionally. But as you can see, there is quite a lot to tamp in a turnout. So that's just the through route. So when we get to the turnout route, right, we can ignore the purple bearers because we've tamped and consolidated them via castle tamping. But the green bearers are the ones we've just packed manually, so then they need a proper squeeze. So we're basically not lifted or lining, but we're just squeezing with the machine to give it its compaction. And then when we get to the blue bearers, which is the first plain bearer, we basically get the design back on. Obviously, the design has to be conducive with our adjustments on the through route. So you need to make sure you take into account what you're lifting and slewing on the through route, and then you can execute your design on your turnout route. As you can see, this is probably one of the biggest examples I've got. You can see how much we actually jack. You can see this was a double junction. The cross levels were absolutely way out, and you can see from that picture how much we actually had to jack that one up. So we come to the first plain bearer, and obviously the machine, so at the bottom where that's the front trolley of the machine, the blue line, and we're basically on the geometry, so we're just cross-level correcting until we come, and you can see the lift on the first plain bearer where we bring the geometry in, And that was 57 mil. So I had the operator saying, God, I've never ever done that. You know, he was flapping a bit, never done that out. But I got out from the machine and yeah, because we corrected the cross level that much, I measured that to be 56 mil. So I can take 1 mil out. But yeah, because we brought it so much back up to cross level, you could see. So we went from 0 to 57 mil lifts over one bearer. I'm quite glad I don't do that on every shift, to be fair. Moving on to untampable bearers. Just excuse me 2 secs. Right, untampable bearers. This is another huge mistake we do. So what normally happens is, tamper comes in, we tamp brilliantly, you know, we do all our plain line, and it comes to our POE, because we don't remove POE, we lift and line, but we don't tamp. So what happens is the machine's axle comes in, crushes it back down, basically. So although we've lifted and line, we haven't tamped. The rate of the rear bogie pushes it down, and then the rear trolley, we're telling the machine that the rear trolley should be on that fine line. However, the machine has fallen into the void, so that it creates an error. So we've done 2 things there. Our most critical area we haven't tamped, so what we've done is tamp the track around it, making it good, and then our POE basically doesn't get tamped, and then we create an error, which then self-perpetuates, and then we create another area. It's called phase shift, and we send the tamper in to do a junction, and we wonder why we have got point failures every 2 minutes, because we're not tamping the most critical bit. Untampable bearers, and what we basically do is remove the POE, double tamp, treble tamp at the correct depth. Sorry about the picture, it was 2004 picture. But that is the staff as the machine's being lifted. You can either remove the POE, or we can lift and hold where we haven't got time if we can. So the machine will lift and line, and the staff will come in. And what will basically happen is we've basically tamped the whole lot and we haven't got any errors. And then the machine will toddle off and we'll all go home happy. Tamping switch diamonds. We basically use geometry. Again, ensure the POE is removed. Switch diamonds are always the worst area. As you can see from that slide, that's right on the switch diamond. However, I had a bit of a bad experience where we basically lifted and lined a switch diamond, and thought we left it great. By the Monday morning, it was failing all over the place, and what had happened was our old friend ballast memory had come in. The POE hadn't been removed for 8 years. We come in, tamp it, and it was back. So what we have to do, if you've got a switch diamond where the POE hasn't been removed for a while, what we did, we lift and held, so you can see the bearer being lifted and held there. And what we came in is basically, we stopped tamping and we just put chippings in, the 2 bearers either side of the knuckle. That's my hand there loading the handheld stone blower. Fortunately now I've got a ticket for that, so someone else can be on their hands and knees in the mud on a Saturday night. So, but basically, yeah, in situations like that, tamping won't, because it's been so long since the POE come off, we basically need to put chippings in. There are 3 systems that we can tamp: HPSS, high drive, and in-bearer clamp locks. Want to have a quick look, because I'm running a bit short of time. Stress transfer blocks. Another massive problem, right? That picture, you tamp 100 times, it's not coming out. BR used to use foam packing for the bolts. And what happened is they changed to epoxy resin, which is basically brittle. And if you have a look in a stress transfer block, you've got 2 rails of different length, so they got different heat, different thermal movements. But the trouble is the epoxy resin's like concrete, and it stops the rail moving. You've got a 25mm bolt and a 30mm hole designed to take the thermal movement, and we're restricting that. So what you basically do is undo or crack the bolts by 6mm, tap each bolt so it all can move with a key and hammer, literally come in with a tamper or slewing jack, line it and torque it back up. And these are some of the results. This is, Alex will know this site, probably took 10 years of his life actually. As you can see on the left-hand side, yeah, you can see the difference it makes before and after. Here's a switch diamond, before and after. And there's the right-hand side of the switch diamond. So yeah, unless you do that procedure right, those alignments aren't coming out. This is one on a full depth layout just to prove as well. So these are heel blocks as opposed to stress transfer. As you can see on the bottom, we went from very poor to good. And on there, it's probably, apart from a spurious reading, it was the best alignment it's ever been since it's been recorded in 1994. So made a huge difference. I'm going to have to really race. Is everyone still with me, by the way? I'm feeling it as well, don't you worry. Just give me 2 seconds. Right, very quickly, I'll just try and get through curved layers. I've got about 3 or 4 minutes. I'd have had a bit longer if my introduction wasn't 5 minutes long, wouldn't I? KH laser, it's basically a straight laser mounted on a trolley, and the trolley compensates for the curve, and it fires onto a receiver on the tamping machine. They call it a T. I don't know why they call it a TV. There's never been any good programs when I've been out on a Saturday night. But what basically happens? There's 2 modes. It's direct and indirect, and all we need is the vertical and a design, basically, and that design to a fixed point. And what happens is the trolley's on our fixed point, the machine works up to it, measures, the trolley goes out and the machine works up and measures, and you just get into a rhythm. And the laser creates a long chord. This is basically displaced to the running edge of the rail. We then apply the design, the adjustments to it, the machine measures the adjustments. We then add our fixed point data, so the machine does its first adjustments to get our design. We add our fixed point data, so not only do we get a design, we get it in the right position. We can then assess it, and if we're happy with the lifts and slews, you can either commence tamping them, or you can do it on a Thursday night and then tamp it on the Saturday. And there you got there, absolutely racing through it. You should be familiar with this now, horizontal levels, but also you can see the mid-table there is our front offsets where we've got with our design, and then we put our polygon points in to say, right, we want that shifted, and you can just see where it's shifted over after we put our polygon points in. So we're getting the design in the correct position. And you can have it in direct mode as well, where you put the fixed point information as you tamp, but obviously you've got to be very confident with your data and make sure you've done it before and are happy with it. And the big beauty of this is the real big it's a long chord measurement. So remember the defects I was talking about before? Yeah, so it gets all your 250 metre chord, measures every 200 mil, every defect's picked up. It's a computer generated chord, so there's no errors, and we get dynamic measuring because of the weight of the machine. So we're not missing out defects. This is just showing you the advantages of 200, every 200 mil on a 250, so everything's picked up. Again, these are good layouts, actually. As you can see, this layout was relayed in 2004. We come in 2009 and actually improved it from relay. So it was already in the good, but as you can see from these charts, not only was it good, we improved it. Once again, big improvements at relay. We come in with curved laser 5 years later, made it even better, and that story says the same thing. Very quick one. I've got the 2-minute nod here. Very quick one, smart ALC. This is available on the 09 machines. We can have it going vertically or horizontally. As you can see, that's in measurement mode. It shows you where the 3 measurement trolleys are. This is it in work mode. The beauty of this is, for the first time, you can actually simulate overlift. So I've put that on there in green. So you can actually, before you actually tamp, you can simulate through and see what exactly overlifts you've come on. We haven't had that facility in the past. And it's also got improved algorithms, what I was talking about before. Factor algorithms. Be dreaming that tonight. Finally, DRP. It's a trace-like recording system that it can record twists, level defects. It's got your track quality on. Again, it's Versine derived, not quite the same as Network Rail, but I have used this in the past to find some defects that I didn't actually see on a night. So it's a much better system than the current DAR. And finally, on the 09, it's got an intelligent DTS system. So, DTS, it's basically artificially induced track settlement. It doesn't damage the ballast. And this is fully flexible. We can fully control the vibration, the vertical load. There is a separate presentation on that, but that's another hour long, and I don't think I'm going to fit that in now, actually. And the advantages of DTS are, it's basically high resistance to track booking, higher CRTs, an extra 5 degrees, which we could all do with, especially on a day like this. Control rapid settlement, increased handback speeds, and, just on the, I'm not going to read that out there, you can all read it, and I think that is just about it, just in time. Thanks very much, everyone, anyway. Cheers.